Assalamu alaikum. Hello, everyone. My name is Khalid Jamiel. I'm a second year medical student. And today's PAL session is going to be pre-recorded and it's going to be about membrane and action potential. So without further ado, let's get into it. So in this session, inshallah, I'll be talking about resting membrane potentials briefly and how they're established. Then I'll be talking about graded potentials, action potentials, and finally, I'll talk a little bit about saltatory conduction. But before I start, my colleague Rawad had another past session that's quite related to this lecture. It's on the electrophysiology of the cell and the movement of ions. And so if you guys haven't watched that yet, definitely watch that before watching this one, as it will help you a lot in understanding this session. So let's get started. First, let's just give a brief introduction to neuron anatomy. I'm sure you all know this already. So these are what we call dendrites, and they're responsible for sensing the stimulus. And then the impulse travels from here to here. So along the axon, this whole part of the neuron is called the axon. And then finally, the axon has axon terminals. Now, this is the soma or the cell body. And in the axon itself, something to note is there's a region at the beginning of the axon. It's called the axon of Philip. And why this is so important is it's because it's the point of the initiation of the action potential in the axon of Philip. Okay. And you also notice some cells called Schwann cells. And these cells are responsible for producing myelin sheaths, which basically insulate the axon. And we'll be talking more about it later on. And finally, between each Schwann cell and the next, we have the nodes of Ranvier, and we're also talking about those importance of those later on. So now let's zoom in into this area. After the axon terminal ends, it synapses with another neuron. This region we call the synapse, and it's composed of a synaptic cleft, which is basically the space between the presynaptic membrane and the postsynaptic neuron. And in the presynaptic, how the message is relayed is that there are vesicles, and once the action potential reaches over here, it releases those vesicles that contain what we call neurotransmitters, which from the name transmit the impulse from this neuron to this neuron, and then an action potential is generated in this neuron, and so the impulse carries on forward. And there are also some basic concepts you have to understand before being able to understand this lecture. Electrical potential difference is a very important term. It's basically the difference between the charge outside and inside. An easy way to remember this is basically the electrical potential difference is the charge inside the cell. So if I tell you that the electrical potential difference is negative, then the inside of the cell is negative. And if I tell you that the electrical potential difference is positive, then the outside of the cell the inside of the cell is positive. Okay, and another term you have to understand is permeability. From the name, it comes from permission, or how much permission the ion has to go through the membrane. So it's the ease with which a molecule can pass through the cell membrane, and this depends on many stuff like the number of ion channels in the membrane. So that's mainly it, the number of ion channels in the membrane. Okay, and then we have to talk about the movement of ions and what affected. So it's affected mainly by three factors. One, as we said, the number of channels on the membrane. So the more channels you have, obviously, the more movement of the ion you have. And then secondly, we have the concentration gradient, which is the difference between the concentration of the ion outside and inside the cell. And finally, we have the electric gradient, which is also the movement. It depends on the charges outside and inside the cell. And if you watch the other Rawat's pal on electrophysiology, he explained those points in depth. So definitely watch those before watching this lecture again. So this is basically describing the concentration gradient. Ions tend to move from high concentration to low concentration, or in other words, down the concentration gradient this way. And positive is attracted to negative, and negative is attracted to positive. So positive ions tend to move towards the negative region, while positive ions tend to move, negative ions tend to move towards the positive region. And this is what we call the electric gradient. And usually we measure those together as something called the electrochemical gradient. We combine both gradients and see where the ion would move. Okay, so those are also other terms that I need you guys to understand. Influx means moving in, Efflux means moving out, and you can guess those from the name in, efflux, exit. So I'll only be using influx and efflux from now on. So make sure you understand what they mean. So let's start with the actual lecture. I'll just touch upon resting membrane potential again because my colleague Rawat has already went over this briefly. So what's the resting membrane potential? It's the electrical potential difference across the plasma membrane when the cell is in a non-excited state. So basically, when the cell is resting, there's no stimulus. It's at the resting membrane potential. And what's the resting membrane potential? It ranges between -70 and -90. But for our sake, it's only going to be -70. So the resting membrane potential is -70. And it's caused by the movement of ions across the membrane and their permeabilities. Okay, so now let's see what establishes the resting membrane potential. So as we said, the resting membrane potential is -90, -70, I mean, and therefore the inside of the cell is more negative than the outside of the cell, and that's what you see here. Okay, so why and how is the inside of the cell more negative than the outside of the cell? So first of all, these are the sodium ions, and we know that sodium ions are more outside the cell than inside the cell. And so according to concentration gradient, where would the sodium ions tend to go? They would move from outside to inside, okay? Because there's more sodium ions outside than inside. Of course, this is if the membrane was permeable. If the membrane wasn't permeable and doesn't have ion channels, then no matter how much the difference of concentration was, if you can't pass through, if there are no channels, there will be no movement. However, assuming that the membrane is fully permeable to sodium, where would sodium go? From outside to inside, down its concentration gradient. And also, let's talk about the electrical gradient. Sodium is a positive ion, and so it would be attracted to the negative region, which is out inside the cell. And so according to both electrical and concentration gradient, sodium would always move from outside to inside. And therefore, if the membrane was fully permeable to sodium, then the inside of the cell would become more positive because sodium is a positive ion and it would make the inside of the cell more positive. So let's summarize that. Sodium ions are more outside the cell than inside the cell. If channels are present, it would rather go inside, as we explained, down its concentration and electrical gradient, and this makes the membrane more positive. So if sodium were to go in, the membrane would become more positive, okay? Now, let's introduce another ion, which is potassium. So unlike sodium, potassium is more inside the cell than outside the cell. So according to concentration gradient, where would potassium go? From inside to outside, obviously assuming the membrane is permeable to potassium and potassium has channels that it can pass through. Because these ions, all ions are hydrophilic, and hydrophilic molecules cannot pass through the membrane, which is hydrophobic, okay? So they need channels. They need channels to pass through. And so if the membrane doesn't have channels for potassium, it won't move. However, assuming that the membrane has channels for potassium, it would move from inside to outside since there's much, much, much more potassium inside than outside. Okay, so let's also talk about that. Potassium ions are more inside than outside the cell. If channels are present, it would rather go outside. This makes the membrane more negative. Okay, so now these two ions, which are the two main ions in the body, they're opposing each other. Sodium wants to make the membrane more positive if there were channels, and potassium wants to make the membrane more negative because it wants to leave. If a positive ion leaves, then the inside would become more negative, okay? And if a positive ion enters, then it will become more positive. So they're opposing each other. And so what did we say the resting membrane potential was? -70. So which one is winning? If these two are in a competition of who makes the cell its way. So potassium wants to make it more negative, while sodium wants to make it more positive. So who's winning? Potassium. It's winning by a lot because the resting membrane potential we said is -70. Okay, so potassium got its way. And why is that? Because we have more Na plus channels or more K plus channels. It's obviously because we have more potassium channels since potassium is winning. Okay, so we can basically say that the membrane is more permeable to potassium, and that's why the resting membrane potential is negative instead of positive. Okay, so that's one of the factors making the resting membrane potential negative. I hope that this factor is clear. Um, As you can see here, the pink ones are potassium channels and the purple ones are sodium channels, and there are much more potassium channels than sodium channels. And that's why the resting membrane potential is negative. That's one of the reasons. So let's talk about more reasons. Now you see those negative molecules, we call them anions. So positive is cation and negative is anion. So these big anions, they're attached to some potassium molecules. And positive plus negative, they cancel out, right? Now, potassium is able to leave the cell since it has channels. However, these anions, they don't have channels to leave the cell, and so they stay inside, okay? So now let's just take these two molecules, or let's take these two molecules, okay? So potassium, let's say, was attached to this anion, okay? Now potassium left, and it only left this anion behind, and this anion can't leave. So instead of zero charge, now the potassium left, and we're left with a negative charge, okay? And that's also one of the things making the resting membrane potential negative, is because we have channels for potassium, and potassium is leaving. However, we're leaving behind the anions, and they can't leave. So initially, their charge was canceled out by potassium, but now, since potassium left, they will have a negative effect on the cell. And that's also one of the reasons establishing a negative resting membrane potential. Okay. So anion is bound to K plus cannot leave the cell. This makes the membrane more negative. Okay. And let's talk about a third thing establishing the membrane potential. This is a sodium potassium pumps, or Na plus K plus ATPase. This is an extremely important channel that you will be dealing with all the time. So I really recommend you get familiar with it. So this is the method of action uh, for this channel. It basically brings three sodium channels from inside, takes them outside, and two potassium ions from outside and brings them inside. So it's opposing the concentration and electrical gradient, and that's why it needs energy, because we're opposing the natural flow of the ions. That's why we need energy to push them out. Okay, so basically we're pushing three positive ions outside, and we're bringing only two positive ions in. And so the net effect is, if you're taking out three and you're giving in two, then the net effect is that we have a negative membrane. Okay, so sodium potassium pumps bring in two positive charges while removing three positive charges, and obviously two is less than three, so you're bringing in less positive charges than you're removing, and therefore the membrane becomes slightly more negative. So all of these factors, all of these reasons are the causes for the resting membrane potential being negative. Okay, and an easy way to remember it would be Nokia 1 2 3. لا, Nokia 3 2 1. Okay, so sodium is N outside, so and 3, so 3 sodium outside, and then potassium is K, I is inside, and then 3 2 1, so 2 is 2 potassium is inside, and then 1 and then A with 1, so 1 ATP is needed for moving 3 sodium ions outside and 2 potassium ions inside. So that's an easy way to remember it if you ever get confused. Now let's talk about equilibrium potential, okay, of an ion. And also this point was touched upon by my colleague Rawad, so you need to attend that before coming to this lecture. Equilibrium potential is basically the voltage at which there is no net movement of ions, and each ion tries to reach its equilibrium potential. Okay, so you see all this maths. Potassium equilibrium potential is minus 90. So if potassium was left all alone and the membrane was fully permeable only to potassium, okay, then the potential would be minus 90. So potassium is fighting and fighting to get the potential down to minus 90, okay? And while sodium is its equilibrium potential is plus 60, so it's fighting and fighting to get the potential to 60. However, the resting membrane potential is minus 70. And why is that? Again, because membrane is much more permeable to potassium, so potassium takes the lead. So that's why the resting membrane potential is way closer to potassium's equilibrium potential than it's closer to sodium equilibrium potential, since the membrane is more permeable to potassium. Okay, so I hope this point is clear. Now let's sum up the factors maintaining resting membrane potential. It's the high permeability to potassium ions, no permeability to anions. So the anions that were bound to potassium cannot leave, while potassium leaves it behind. Low permeability to sodium ions, because if sodium was left alone, it would try to get the membrane potential to plus 60. But we don't have much permeability to sodium, not as much as potassium, and therefore uh, we have a negative resting membrane potential. And finally, the sodium-potassium pump, as we explained. Now, this is how an impulse is generated. This is the sequence of events. First, we have a graded potential, and the graded potential is formed from a stimulus, and we'll get into this in a bit. Then we have something that's called the threshold. So the threshold is basically the membrane potential at which you can generate an action potential. So if you reach minus 55, then an action potential will be generated. If you don't reach minus 55, then no action potential will be generated. And we'll talk about this slightly later on. And then action potential obviously is the upstroke, and let's get into each one in detail. So basically, this is the sequence of events. A graded potential happens from a stimulus. If the threshold was reached, then action potential would happen. If the threshold wasn't reached, then you won't have an action potential. So graded potentials, they're a change in the electrical potential on the membrane of an excitable cell, example like a nerve cell, in response to a stimulus. So a stimulus causes the graded potential, and the magnitude of change is proportional to the strength of the stimulus. Now, this is a very important point. The main difference between graded potentials and action potentials is graded potentials, the magnitude varies according to the stimulus. So if the stimulus was just a slight, barely touch, you will sense it, but the stimulus won't be as strong as مثلا fire or a pin uh, on your hand. So pain, for example, has a very strong stimulus, but a breeze from wind won't have as strong as stimulus. Okay, so that's the main difference between graded potential and action potential. Action potential is always the same strength. It's always the same magnitude. A graded potential's magnitude depends on the strength of the stimulus. Uh, so they may ask you in the exam, what's the difference between graded and action potential? And the answer would be, in a graded potential, the magnitude of the graded potential depends on the stimulus and the strength of the stimulus. However, the action potential, it's independent from the strength of the stimulus, and it's always the same magnitude. Okay, so this is just the resting state. This is the cell at rest, and then a stimulus occurs here, and the graded potential happens. Now, did this graded potential reach the threshold? No, then there will be no action potential. However, if the stimulus was strong enough to raise the membrane potential from minus 70 to minus 55, then if the threshold is reached, then we will have an action potential. But let's explain how graded potentials happen in the first place, okay? So let me show you in the diagram. So this is a sensory neuron, and it's synapses with a dendrite of another neuron over here. Okay, and you see those neurotransmitters. They have some things, or they're called ligands. Okay, so those neurotransmitters, they're called ligands, and these ligands bind to this dendrite, the synapse with this dendrite of the neuron, and it opens what we call a ligand-gated cation channel. Okay, so what does ligand-gated cation channel mean? So it's a channel that has a gate, and this gate opens once a ligand binds to it. Okay, and where does this ligand come from? It's from the sensory neuron that released it from the synapse over here. Okay, so once this ligand binds, these channels open and they let cations in. Okay, cations, whether it was sodium or calcium or any positive ion, it lets all positive ions in. It's not specific to any positive ion, lets all positive ions in. Okay, and so that's how it's done. Now, the stronger the stimulus, the more neurotransmitters and ligands will have, and the more channels will open, and that's why there will be a greater change in the membrane potential. Okay, so the strength of the stimulus is determined by the number of vesicles it released, and the more ligand-gated channels open, the more the change in the membrane potential, and the more likely we'll reach an action potential. Okay, or we reach the threshold. So basically, stimulus or neurotransmitters open channels that allow an influx of cations, and this channel is called ligand-gated cation channel, and this makes the membrane more positive. And if the membrane potential rises from -70 to -55, then the stimulus is strong enough to cause an action potential. Okay, so so what event occurs when the neurotransmitter is excitatory? We said the ligand-gated cation channels open, allowing sodium and calcium mainly to go in. Okay. Now let's talk about the main part of this lecture, which is action potential. Okay. So action potential is a rapid sequence of changes in the voltage across a membrane. And how is an action potential triggered? It's when the graded potential is strong enough to reach the threshold. Okay. Now, the action potential has three phases. One is called depolarization. So polarization just means negative, okay, and D means less, so less negative. So you're making the membrane less negative, or in other words, more positive. And how do you do that? By the opening of ligand-gated cation channels, okay? And then a lot of events happen, and we'll get into exactly what happens, okay? And then we have the second phase, which is called the repolarization. So this is less negative, and then this is repolarization, so negative again. So after it reached a very positive membrane potential, we have a phase that's called repolarization to return the cell back to the resting membrane potential after the action potential is finished, okay? And then we have hyperpolarization, which means more negative. So we're making it even more negative than the resting membrane potential. So this is an action potential diagram, and we'll get into each part of this diagram and explain exactly how it happens and exactly what happens inside the cell. Okay, so this is the stimulus, this is the graded potential. If the graded potential fails to reach the threshold because the stimulus isn't strong enough, it just drops back and no action potential happens, and خلاص, the cell continues at its resting membrane potential. If it was strong enough, however, to reach the threshold, an action potential would be generated. This is the first phase we call depolarization, and you can see the membrane potential jumps from -55 to 30, and then we have the second phase, which is repolarization. So the cell goes back to resting membrane potential, and then once it gets back to resting membrane potential, we have the third phase, which is hyperpolarization, in which the cell goes even lower than resting membrane potential, back down to -90, and then it goes up again to the resting state. Okay, so let's see exactly what happens in the cell. But first, there's a very, very important channel. We need to know exactly how this channel works, which is the voltage-gated sodium channels. So you see the difference. This is voltage-gated sodium channels, so they're specific to sodium, and the channels responsible for the graded potential were voltage-gated cation channels. So it wasn't specific to any ion, and that's a very high yield question that comes a lot, and know which channel causes the graded potential or which channel causes an action potential. This channel is responsible for causing the action potential, the depolarization phase at least, and the cation channel is responsible for the graded potentials. Don't get mixed up. So this is the basic structure of the voltage-gated sodium channels. It has two gates. It has the activation gate and the inactivation gate. I think in the slides it's M and H gate. Okay, so basically what happens is once a threshold is reached, the activation gate opens. So initially the activation gate is closed. It's in this conformation when the resting membrane potential. And once an action potential is generated, the activation gate opens, and there's a huge influx of sodium. The sodium is just waiting for a chance to get in. And as soon as you open this gate for it, it will rush in. There will be a huge influx of sodium, and it will raise the membrane potential from -55 to +30. Now, once +30 is reached, the inactivation gate now closes. Okay, and it's in this conformation. Okay, and then repolarization happens, and we'll get into how that happens in a bit. And then once the resting membrane potential is reached again, it's back to this confirmation. The inactivation gate is goes down, and the activation gate closes the gate again. Okay, so let's get into a little bit detail. So now let's assume a stimulus happened and threshold was reached. Now the sodium ions over here, they're trying to get in, but they can't because why? The inactivation gates are closed. Okay, and this is indicative of an action potential that happened over here. But let's see over here. Now this is a no these are open channels, okay, which means the threshold was reached over here. Okay, so the membrane potential was minus 55. Now the sodium ions, they rush in inside, okay? And then over here, this is the confirmation of the resting membrane potential in which the activation gates are closed and the inactivation gates are closed, okay? So this is once the threshold is reached, the voltage gated sodium channels are open. This is once the resting membrane potential is reached and uh, and the activation gates are closed. And this is after an action potential maximum or peak is reached, and this is where the inactivation gates are closed. Okay, so let's talk about the depolarization and the permeability of ions. Okay, so in the depolarization phase, the permeability for sodium is much higher than the permeability of potassium, and that's the only reason the membrane potential is able to reach such a positive value of plus 30, because the sodium ions are rushing in quickly because they have full permeability. The channels in this region are open, and so the sodium rush in, making the membrane potential up to plus 30. Okay, and so the permeability for sodium ions over here is high, and the permeability of potassium ions is low. Okay, because there are no change in the potassium channels. They're just leaky channels that uh, let the potassium channels go out slowly, and there's no change in them. However, there's a huge change in the permeability for sodium because a lot of voltage gated channels are present and they're all open at once, and there's a huge influx of sodium, and therefore the permeability of the membrane in this state, in the depolarization state for sodium, is much higher than potassium. This is a very important concept and it's asked about almost every year, the difference between the permeability to different ions in different stages. Okay, now let's talk about what happens to potassium. Okay, we have voltage gated potassium channels now. Okay, so the voltage gated sodium channels are responsible for depolarization, and now once we reach maximum and no more sodium channels are coming in because the inactivation gates closed, now we have the action of the voltage gated uh, potassium channels. Now this is just the other side of the cell. Let's assume this is a circular cell. This is outside the cell, and this is also outside the cell. Now once uh, the sodium channels cannot get in anymore, we have the voltage gated potassium channels which open at the membrane potential of positive 30. Okay, once positive 30 is reached, which is the peak of the action potential, the voltage gated potassium channels open. And where did we say potassium would move if the membrane was fully permeable for it? It would move from inside to outside the cell. So if a positive is moving from inside to outside the cell, then we'll have a negative membrane, and that's how the membrane potential becomes more negative, or what we call repolarization. Okay, so it all depends on which channel is open and what ions are moving inside and outside. Now you'll notice that the configuration of the potassium gated channels is different from the sodium one. It only has one gate, and this gate opens once plus 30 is reached, which is the peak of the action potential. And that's why action potential cannot go over plus 30 and cannot increase in magnitude no matter how much the stimulus was strong. Because at positive 30, the sodium channels close and the potassium channels open. So sodium channels stop coming in, no more positive membrane, and the potassium ions start leaving out quickly, and therefore it drops down the membrane potential quickly, because leave the moving out of positive ions makes the membrane negative. So I hope this point is clear. Now, let's talk about hyperpolarization. One thing what's special about the sodium channels is this configuration, and it's having two gates, the activation and the inactivation gates. And I hope by now you know how that works and which gate is open at which potential, because that's very important. They'll ask you at a potential of مثلا minus 70, which channel is open, which gate is open and which gate is closed, and minus 70, which is resting membrane potential, for example, the activation gates are closed while the inactivation gates are just locked. Okay, so you have to know how the channel looks like in each potential, which is minus 70, and then at the threshold or the depolarization state, and then once it reaches the peak or plus 30. Okay. Now, the special thing about the potassium ligand is that it closes slowly. Okay. So once it reaches minus 70, you'd think it closes because خلاص it reached the resting state. No, but it doesn't. It closes very slowly. Okay. And so potassium channels will keep going out because it has a chance to. It will keep going out until it reaches its its equilibrium potential. Potassium's equilibrium potential. Because if you remember, we said that potassium's equilibrium potential is minus 90, and it will fight and it will do whatever it can to get it down to minus 90. Now that it has the chance and the potassium gated channels they close slowly, they have the chance to leave even more, even after the resting membrane potential. And this is what causes the hyperpolarization state. And obviously the permeability for sodium is still low because خلاص, sodium channels will close at minus 70. And if you go lower, it won't open. Obviously, you have to reach minus 55 for them to open again. Okay. And potassium, the permeability for potassium is much higher than sodium because, as we said, the potassium voltage gated channels are slow to close. Okay. I hope this point is clear. If you have any misunderstandings or any questions, you can always contact me. You have my number at the beginning of the slides. Now let's talk about what happens. We spoke about the action potential. Now, how does the action potential, or how is the impulse going from one cell, from one neuron to the other? After the axon is finished and action potential happens all across this axon, you reach the axon terminal. And if we zoom in here, we said we have synapses. And let's zoom in even more. So at the synaptic membrane, we have voltage-gated calcium channels now. Okay, so we have voltage-gated sodium channels, which are responsible for depolarization. We have voltage-gated potassium channels, which are responsible for repolarization. And then we have voltage-gated calcium channels, which are responsible for releasing the vesicles from here, from this presynaptic membrane to the postsynaptic membrane. So how this works is the action potential reaches over here, and it makes the membrane over here positive. And this causes the voltage-gated calcium channels to open, and calcium goes from inside to inside, from outside to inside. And calcium always has this property of making things stick together. So it makes the vesicle move to the membrane, presynaptic membrane, fuse with the membrane, stick to it, and what we call exocytosis of the neurotransmitters, and that's how it's released from one neuron to the other. Okay, so let's quickly recap. In a graded potential, what's happening? Ligand-gated cationic channels open. Cationic, so it's not specific to any ion. All cations can enter. Okay, and this is due to a stimulus, and the size of the graded potential depends on the strength of the stimulus. Guys, everything I'm saying right now in this summary is extremely important, and it's asked about a lot. Okay, so you need to know exactly what event is happening in each stage of the action potential. So in the graded potential, it's caused due to a stimulus. Its size or the magnitude of the graded potential, or how much the membrane potential changes, depends on the strength of the stimulus. And it happens due to ligand-gated cationic channels opening. Cationic is not specific to anything, so any cation can enter. Now, if a threshold wasn't reached, then خلاص, there's no action potential, it just dies down. If the threshold was reached, then you'll have an action potential, and this is the depolarization state. And what happens in the depolarization state? Voltage-gated sodium channels open. Okay, so the activation gates open, and now you don't have neither the activation or inactivation gate on. Now, once we reach the peak, we'll repolarize. And what are the events happening? Two events this time. The voltage-gated sodium channels close because the inactivation gate closes, and also the slow voltage-gated potassium channels open, allowing potassium to leave from inside to outside rapidly, making the membrane more negative again. And then once we reach the resting state, do we stop there? No, we don't, because slow voltage-gated potassium channels, and it causes to hyperpolarize because the potassium channels are slow to close, and potassium just takes the chance and leaves, and it goes as close as possible to its equilibrium potential. And then obviously, how does it come up from here to here? All the things you remember that we said establishes the resting membrane potential. Sodium channels have low permeability, potassium channels have high permeability. The sodium potassium ATPase, that's the main thing. The sodium potassium ATPase is what brings back the resting potential from here to here, okay? And then I will wait for another stimulus to come, and then maybe another action potential will happen. So this is just a summary slide. If you guys know everything over here, that's very good, okay? So this is a question: what happens to the membrane potential at the peak of the action potential? We said it's closest to the potential of sodium equilibrium potential. Obviously, guys, it's too late now, but I wanted you to pause before I show the answer. So hopefully you understand why the answer is correct. Okay, because the sodium equilibrium potential is 65, and this peak is as close as it can get. Plus 30 is as close as it can get to the sodium's membrane potential. It can't go above 30. Why? Because the inactivation gates close over here. Okay. Now let's talk about another important concept, refractory periods. So refractory periods are a state of recovery that occurs after a neuron has fired an action potential. Okay, so let's get into it. So refractory periods are two types. One, absolute refractory period, and two, relative refractory period. Okay, so in the absolute refractory period, as the name suggests, you absolutely cannot have any other action potential in this period. Okay, no action potential, and because the sodium channels are inactivated. خلاص, at plus 30, the sodium channels are inactivated, and you can absolutely not have another action potential fire. Then the sodium voltage gated channels are closed by the inactivation gate, and they won't open unless the resting membrane potential is reached again. Okay. And so if you don't reach the resting membrane potential again after plus 30, خلاص, no more active potential, and this is called the absolute refractory period, and we'll get into more detail. Now we have another type, which is the relative refractory period. It's not impossible to reach an action potential, but it's very difficult. You need a very strong stimulus. And why is that? Because now that in the relative refractory period, that's going to be in the hyperpolarization period. Once we reach the resting state, theoretically speaking, the sodium channels, the inactivation gates, they go back down, and the activation gates close. But it's possible to get an action potential, theoretically speaking. But you'll need an extra strong stimulus. Why? Because we have hyperpolarization. Okay, and let's explain it over here. This over here is خلاص. This is absolute refractory period because the inactivation gates are closed, and no matter how strong a stimulus you have, you won't be able to open them unless the resting membrane potential is reached again. Okay, so this over here is called the absolute refractory period. That's obviously because the voltage gated sodium channels are closed. Now, in the hyperpolarization period, this is the relative refractory period. And why it's theoretically possible to have an action potential again, okay? Because خلاص, we're over here, okay, in the hyperpolarization state. We're over here. We're in the normal configuration of the sodium with voltage gated channels. And theoretically speaking, we can have an action potential, but it's more difficult because the resting potential, I mean, the membrane potential is way further than from the threshold than when you're at resting state. Okay, so from resting state, you only need to jump from minus 70 to minus 55. But in the relative refractory period, which is hyperpolarization, you need to jump from minus 90 to minus 55. So that's 20 millivolts more, and therefore you'll need an extra strong stimulus for an action potential to happen over here again. Okay, it's possible, but you need a very strong potential. That's why we call it relative refractory period. However, over here, no matter how strong the stimulus was, you won't be able to generate an action potential. This is just a potential summary and channel summary. Go through it quickly. Now, let's talk about saltatory conduction, or how action potential is transmitted through the axon. We know how it's generated in one region, but we don't know how it travels through the axon and reaches the axon terminal. And we also know how it reaches from the axon terminal to the next neuron, hopefully by now. Okay. So the way an electrical impulse skips from node to node down the full length of an axon is called saltatory conduction. So the action potentials they don't go like this just straight. They jump from node to node. And this is the importance of Schwann cells and nodes of nanometer. It is faster than the continuous conduction of unmyelinated axons. So this is what continuous conduction would be, just an action potential traveling like this. But this is saltatory conduction, jumping. And I like to think of the analogy of a turtle and a rabbit. The rabbits jump and they're much faster than turtles. Okay. And so let's see what happens exactly inside the cell. Now, this is assuming we don't have myelin sheath. Okay. This is just continuous conduction. Now, after the action potential ends here, an action potential is generated over here because the sodium channels that came in, they diffuse towards this direction. And they raise the membrane potential over here. And therefore, this area reaches the threshold, and this area opens its voltage sodium gated channels, and then more sodium comes in, and then whatever comes in over here will go over here and then open these channels. So this is how a continuous conduction would happen. Now it's very similar in myelinated cells. So these are myelinated cells. This is the myelin sheath. It's an insulator. In these areas, we have no channels. No channels. We don't have those channels, okay, in these areas. And so why is this faster and much more efficient? Now let's say this sodium channel opened, okay, and then we don't have any uh, channels next to it, okay? So everything that comes here is concentrated, okay, and it moves quickly, more quickly, because there are no channels taking the sodium ions in, okay? So uh, it goes a lot faster from here to here, and it's in a higher concentration, okay? So it jumps, poof, action potential happens here, and then to the next one, and then to the next one, okay? This is just an explanation of what I said. So saltatory conduction, myelin acts as an insulator, positive charge maintained as it moves to the next channel. So they're concentrated and they move quickly to the next channel. Channels are only present in the nodes of Granvier, so the areas where there's no myelin. Okay, so action potentials jump from node to node, node to node, node to node. Okay, and channels are only present in the nodes of Granvier. Less number of action potentials are needed to need to be generated, plus more energy is reserved. That's also a very important importance of saltatory conduction, because let's imagine we have this, between this and this, we have to generate an action potential. That takes a lot of energy from the cell. However, if it's fewer action potentials to reach the end, because we have fewer points of where channels are, then we're reserving energy. And there's obviously much, much faster conduction. So that's it for the lecture. This is a short, very beneficial video so that you can watch that sums up everything. And if you have any question, please don't hesitate to contact me. I know this lecture may be a bit rough to get in the beginning, but it gets easier, and practice as many questions as you can, and inshallah it will be easy. So that's it for me. Assalamu alaikum.